Thank you for the introduction. So my name is Joohyun Kim. I am Senior Data Scientist at MyFitnessPal, now part of the Under Armour Connected Fitness. So what I'm going to talk about today is called iRIS, which is a system of the large-scale food and recipe recommendation using Spark. So let's get started first with who are we. So we are MyFitnessPal. And we started as a startup company in San Francisco. We built a diet tracking app, which provides users with nice values for whatever they track with our app for whatever they eaten for the day. And we help users to keep their fitness goals. And we are #1 in health and fitness category. And we have 85 million plus registered users, which is by far the largest single digital health and fitness community. And we have around 7 million food databases. And also we have 14.5 billion plus food logging event, which is coming from our registered users, which is by far the largest food and nutrition database in the world. Now we are acquired by the Under Armour. In Under Armour, including MyFitnessPal, we have 4 different apps, which are kind of more focused on the workout domain. But in total, we have more than 120 million users in total. And as you all know about the Under Armour, it has a very strong presence in the e-commerce and the retail. They have a very strong retail sales. So in terms of market size and the number of sales, they are kind of #2 in the Northern America, just next to Nike. So you may be wondering that why Under Armour? Isn't Under Armour is a product company? Yes, it's true. But if you're interested, I highly suggest you to take a look at this article, How Under Armour is Becoming a Tech Company. So Under Armour is recently heavily invested in acquiring different app companies, including MyFitnessPal. So they invested more than $700 million for the acquiring these companies, so that they definitely shape as a leader in the digital health and fitness market. So we are definitely seeing Under Armour is a whole tech company. Also, I personally see the Under Armour is a data company. We have so much data across all different domains. The first and foremost important thing is from MyFitnessPal, we have food and nutrition data, which has already told you that we have 14.5 billion plus data points from the users. We have 7 million plus foods and 38 million plus recipes data, which is also kind of by the far largest data in the world. And you can still think about the whole lot of user diet history and user preference over the foods. That's really powerful. And another category is the workout data. The workout data that we have across 3 other apps, such as MyFitness, and the Mondo, and the Under Armour Record. They are more focused on the workout setting, like having GPS tracking data. So for the workout domain, we have time series GPS data, definitely. So we track the classification of the run, ride, and walk data. We have tracking the active time of the day and the sleep pattern. And even from the MyFitnessPal side, we track down 380 billion plus calories burned and 1.2 trillion minutes of the exercise logged. And the last part of the data that we are really keep focusing on is retail e-commerce data. You can think about all the product purchase transactions and user preference over the different styles of products. Then all these pieces have a really big synergy out of it. So we think this is a really kind of big opportunity for us, and we shape it as a data company. But today, I'm going to focusing on explaining food and nutrition side, which is MyFitnessPal's core area. So let's talk about it. So let's talk about the importance of data in other companies. The successful companies like LinkedIn, Facebook, Netflix, or Google, Amazon, they have all their own data products, like a recommendation system. So what they do is using the power of data, they build a kind of product, and they help the users to keep engaged within their framework, within their platform, and drive kind of new numbers like MAU and DAU. Really nice example is definitely LinkedIn. LinkedIn's PYMK, people you may know, is the kind of classic example of the recommendation system. So it helps LinkedIn's users stay within the network and help them growing their network. And it was really effective and successful. So what we want to do here is, like these companies, we want to build a nice data product, which is a recommendation system, so that we can keep our users within our platform for a longer time, and we want to drive some new numbers. So let's talk about the foods. So I personally think the biggest concern of life is kind of choose what to eat, actually. We think at least twice a day, we think about what to eat for the day, for a meal. But there's a whole different considerations we are kind of personally thinking about. Definitely is a taste, and we want to eat a healthy food. And there is some kind of a dietary restriction personally by some medical conditions or some cultural differences. And there's also definitely some taste preference with no reason. So some people prefer one food, the other, or vice versa. So then how do we choose it? We got recommended by kind of various sources. So the traditional way of getting the recommendation is something like a word of mouth. We are hearing recommendations from our friends or family, which is pretty personalized, which is great. And also we see the reviews and blogs such as Yelp, so that we see the restaurant reviews and decide to go for there and try out some foods. Or we get some expert advices such as expert article on the magazines. So all these things we can think about typical ways of getting recommendation. But these are kind of pretty limited in terms of it doesn't consider every aspect, and it's biased in terms of opinion, and it is also lack of source in terms of, so it doesn't kind of consider the different things around. So besides of these typical ways of getting recommendation, we want to build out a more systematic way of getting the recommendation. So the one idea which has been quite a few years around is the collaborative filtering. Collaborative filtering is simply the predict how a user may like a new item based on the prior user behaviors with a similar preference. So in our case, we have constructed the large food user food log counts table. So let's predict for the Jane for her preference over apple or melon. So we look at the similar users. Let's see John, which has pretty look similar. And let's for the melon, and I think Jane may like a melon. So this is kind of basic idea. In order to solve this problem, there has been lots of algorithms out there so far, but one of the famous algorithms has been out there for a few years is matrix factorization, which is basically you can think of filling in the missing entries in the ratings table, which in our case is user food log counts matrix. So the problem becomes formulate this as a two-factor low-rank matrix factorization problem, so that we divide the ratings matrix R into the two matrices, which is the user and items. So you may notice that the user and items has a very small dimension, which is a really low rank, which we call feature, so that it can capture the kind of generalizability of the user and item patterns. So now then becomes objective is to minimize the root mean square error between the raw matrix of the ratings matrix that we have and the predictive matrix between the multiplication of users and items. So that's that simple. But the problem is this setting works pretty well with the explicit ratings. The explicit rating means that which is typically available for the movies on song reviews or some item reviews in e-commerce, which typically users give by 1 to 5 rating so that they like or dislike they like or dislike this particular food, particular item. But in our case, in our food logging events, there is no such kind of negative feedback for the foods. That only we see is the logged food events, actually. So the problem here is we cannot assume the zero count appearing in the ratings metrics as a negative feedback. But there's a really nice paper that we also use as a reference, is color filtering with the implicit feedback data set in 2008, which exactly solves this situation. So the basic idea is, oh, sorry. Yeah, that's maybe some kind of some wrong format conversion for it. But so the basic idea is construct the binary ratings matrix P instead of the row ratings matrix R, so that we can factorize not against for the row ratings matrix R, and we can factorize against the P and get the X and Y. So now the problem becomes simple. So now we wanted to get the user matrix X and items matrix Y, try to optimize against the P. But doing it at the same time is very hard. So here comes the idea. The iRIS encoder alternating least squares that we are also using it is, let's fix X or Y, and let's solve for the other. And the idea is fix one thing, and the problem becomes just solving the system of linear equations. So we are starting with the random initialization of Y, and then solve for the X, and vice versa. And the nice property of this algorithm is it is known to be converged very fast. And in a typical large-scale data set, it is converging like up to 10 or 20 iterations. So that's good. But the problem always is a scalability. So we are talking about the ratings metric size of the 85 million users with the 7 million foods, which is roughly like 600 trillion entries. It's just basically impossible to fit into a single machine. Even the sparse representation is we are talking about billions of entries. But ALS has a really nice property of can be easily parallelized with the MapReduce framework, but with the sharding and using a mapper and reducer. But we don't really care about it because Spark MLlib has a really nice implementation of the parallelized version of the ALS is already ready to use. And it's even faster with the data frame, and it can be handled with this simple single line of code. So let's take a look at the whole pipeline first. So in order to make the system end-to-end, we need to first load those our data, which is a log food data, to construct the ratings matrix, which is a user food log counts table. And using the ALS algorithm that I explained earlier to actually the prediction step, the predicted user preference by the matrix factorization. And then the final, but the kind of, you can say the most important step is the generating top K food recommendations. This step is often to be ignored, but so without that, we don't get any kind of recommendation. So it's very important. So let's talk in detail about the generating top K recommendations. By nature, it's just seems trivial because it is just getting the recovering the ratings metrics by multiplying the metrics user and items x, y. It's also a little bit broken, but after that, we are getting top K for the every user. But think about the operations. So basically what is having is retrieve all the matrices per each user. And then take the per each user, we get the top K items for the individual food preferences, which requires roughly the same order of constructing whole matrices, which is around like 600 trillion entries. So this becomes a kind of major bottleneck for our case, for the entire pipeline, and there's no easy way to get around this computation. But with the help of Spark, we got it computed pretty reasonable amount of time. So let's talk about some numbers. We own the Spark cluster with around roughly 72 nodes with the 2 terabyte of memory, and we believe that it's one of the largest clusters running in production. And in terms of data set, we already talked about the user is 85 million and item is 7 million. The ratings, the full log count matrix, which is aggregated over the user food, we have is about 6.5 billion points. In terms of time, the AS itself is taking about 4 hours, which is pretty good and which is pretty fast. And generating the top K food recommendation, which was a major bottleneck, which was taking about 48 hours and up to like 72 hours. And with the help of Spark, we are experiencing more than 20x speed improvements over Mahout in the conventional Hadoop cluster based on our previous experiences. So there are kind of major advantages using Spark in our cases. The first thing is definitely the faster development cycle. The MLD provides a really nice, commonly used machine learning algorithms with easy parallelization. And with the recent data frame, it is even easier to construct the whole machine learning pipeline. And also even easier to load and export data in and out of S3 and Redshift, which is our main data storage, with the all kind of functionality of supporting JSON and all other different formats. And another benefit is the faster model optimization. So by nature, it is providing in-memory distributed computation, which makes us for the faster model training testing time, and which also allows us a significant reduction in the parameter tuning optimization on the validation data set, so that actually to market time is drastically reduced. And the easy scalability. Only we have to do is just by launching more worker instances, then we can get the scalability that we want. Also, for the overall faster pipeline, that enables us frequent model updates. So we can reflect user preference changes more often. So this is some sample food recommendation from our system. So I'm Korean. A lot of foods are all bunch of like Korean foods. But you see the recommendation results, you're seeing Korean foods and Japanese foods or other Asian foods. So which makes total sense to me. And the system actually works. So I want to talk about the extension, which is the recipe recommendation now. The recipe, so we are really heavily interested in recommending recipes, but why recipes? There are clear advantages of using the recipes for the recommendation because it has a richer data and it is complete food and home cookable. And it is highly customizable with the personal preference and restrictions. But there's one problem with the recipes. In our data model, recipes are by nature not public actually, which means recipes are not shared across the different users. Which was the kind of product decision that we made because recipes are highly customizable, so we don't want to show all the users that all different customizations of the individual user made to every user. So by nature, I mean, we cannot get the standard user item ratings metrics for the recipes. So that's a problem. So we cannot run the collaborative filtering on top of the recipes. But the solution we have is let's use the current food recommendation pipeline, and let's make it an extension to the additional similarity step to food and recipes. So let's recommend the recipes by the similarity of the recommended foods. So here's the pipeline extension. So on top of the food recommendation pipeline, we add food recipe similarity computation. And the final step will be the generating top K recipes from the food recommendation rank and recipe similarity rank. I'll talk about it in detail. The first step is I talked about we are going to use the food and recipe similarity. But by using the similarity means we are going to use the nearest neighbor computation over the food and recipes. But the problem is a naive computation of nearest neighbor algorithm is the order of n squared, which is nearly impossible with the current data size that we have. So the one idea that we got is actually locality sensitive hashing. So the basic idea is it is hashing the similar items into the same buckets with a very high probability with a given similarity metric, so that now becomes the nearest neighbor computation much faster. And also, the computation is becoming just looking at doing the similarity computation within the bucket. And considering the bucket size is pretty small, that the overall computation is getting much faster. And we have a kind of already Spark implementation in the GitHub, and we use that. It was pretty easy for us to extend. So the final step is getting the type K recipe recommendation. The basic idea is to order by the combined rank, which is the sum of the full recommendation rank and the recipe similarity rank. The reason why we are using those combined rank instead of the combined similarity score is actually we are trying to handle those similar scores of these the food and recipe, but the similar score is kind of fluctuating fairly. Even though we normalize it, it doesn't really quite in the kind of similar scale of the recommendation metric. So in this way, we are getting like a much more stable results for the recipe recommendation out of the food recommendation. So that's a kind of sample recipe recommendation, but let's skip for this now. So I want to talk about a little bit different topic. So this integrating with the taste profiles is coming out of our intern projects. So we built a machine learning classifier that outputs the probability distribution over 6 different taste categories, which is basically really simple. The nearest neighbor classifier performed over the feature vector that we have, which is combined the semantic word vector, and the numeric nutritional value vector, which was performing pretty nice, around like 87% accuracy on the separate health data set. And it is working as additional metadata for our entire food data set. And the nice thing is that this could be an easy extension to our current recommendation pipeline. This can be, recommendation results can be further filtered or reordered by the personal taste preferences, so which is really great. And with the even Spark, those kind of data integration is kind of much faster. So there is kind of no hassle, and we don't really worry about the time for it. Let's talk about some problems. So typical recommendation system, and same as our case as well, is facing the cold start problem. There are kind of two kinds of cold start problem, which is a new user and the new food item. For the new user case, it's much more important for us because we want to recommend something even for the new users. But for the new food item, it's kind of less important because those new foods may not be popular. So whenever they got popular, then they kind of by naturally it will be recommended. So, but how to solve this problem? There are like one classic way of solve this problem is making a hybrid with a content-based recommendation. So the idea here is constructing the basic profile for every users by asking some questions. And let's recommend some foods based on the feature similarity between those profiles and the food data we have. It may also solve those new food item problem because based on kind of what features that we have for the new items, those new items may be also recommended as well to the new users. And the second solution that I really like personally is with the help of Spark, we can run the pipeline more often. So the whole pipeline now it is done within like 3 to 4 days. We can run the pipeline every week or so. So for the new users, let's just recommend the top popular foods. And whenever we gather some data for the week, then these new users will get more and more relevant recommendations as time goes by, which is really great. And one another kind of possible extension that we are currently work in progress is collaborative filtering over the aggregated food cluster. So I don't know how many of you actually attended the Spark Summit East this year, but there's a talk that my colleague Hassam presented about the project. It's called the Gold Food Project or the Verified Food Project. The basic idea is that in our app screen, we want to add a little check mark for the for the food information that we are absolutely sure about. The algorithm side, we are using Spark to getting through the thorough clustering, the food information is patched together within the cluster so that we are really fine-tuning the food data with a really very high confidence. So the benefit is that now we have a really high-quality, clean food clusters. We can recommend users with a really high-quality food first. And then second, we can recommend the representative food cluster instead of the individual near-duplicate variations, which actually significantly reduces time due to the reduced dimensions. So now we said that we have 7 million foods, but after those aggregated food cluster, the dimension is kind of much smaller. So we can run this pipeline more often. So far, we kind of talked about all the pipeline and things. We never talked about the product feature. But let's talk about a little bit about product feature that we are really kind of considering. So this is the current app screen for the iOS that showing that suggesting the users with the frequently paired foods, which is basically for the coffee, just recommend bagel or something like. But these kind of pairing of foods with a single meal even depends on individual users' own preference, and also it differs greatly by the cultural difference. The really simple way to do, and it's actually the current way of the current iOS client is implemented, is suggest the popular foods based on the current stats per individual basis or the overall users. But we are currently thinking of utilizing this whole framework of the recommendation pipeline to capture the better personalized experiences, best personalized preferences for the recommending per food items. So in summary, I presented like a Spark-powered machine learning pipeline for the food and recipe recommendation system. We got the major benefits using Spark. First one is a faster computation time, which leads to the faster development cycle. And it really helped out data scientists like us to focus on really core problems. And the easy extension is possible by just simply adding the additional data processing steps without much worry about the scalability. And the second thing is we think that it is just only a starting point. I present that our food and recipe recommendation system, but think about it as a whole Under Armour family. We have a whole different data sources like a workout and music and retail and e-commerce data sources. So we are thinking of extending this current recipe recommendation pipeline to extend to other data sources to make a synergy out of it. So that's about my talk. Thank you.
Thanks. So due to the time, I'm going to actually ask that you ask questions offline, if you don't mind.
Sure.